Okay, welcome everybody. So in this video, we are going to continue our work with inner product spaces and look at more general inner product spaces beyond just Rn. So now we're going to consider the vector space, which is P4, right? So this is polynomials at most degree 4. And inside of P4, we have a subspace P2, polynomials of at most degree 2. So this subspace is spanned by these three vectors, 1, t, and t squared. So what I'd like to do is take this basis for this subspace of P4 and find how we can generate an orthogonal basis for this vector space going through the Gram-Schmidt process. So what's really nice about inner product spaces is that they allow us to use the same geometry of lengths and angles that we've discussed with Rn in these more abstract spaces. And so for this inner product that we're going to put on P4, the one we've discussed that we're going to keep using is the one where we say the inner product of polynomial P and Q is equal to the sum of the values that I get when I evaluate P and Q at -2, -1, 0, 1, and 2. And then take the product of those polynomials when we evaluate them at the same t value, and then add up the 5 terms in that sum. So we've worked with this inner product. So if it's been a while since you've looked at this, take a look at the previous slides and some of the videos where we discussed how we can calculate lengths and determine whether these polynomials are orthogonal to each other. So for example, the inner product of 1 with itself gives us 5. The inner product of t with itself gives us 10. T squared inner product with itself is 34. The inner product of 1 with the polynomial t is 0. So these two polynomials are orthogonal to each other. The inner product of 1 and t squared gives me 10. So these two polynomials are not orthogonal to each other. And then the inner product of t with t squared, that gives us 0. So using this inner product, we can find out the relations between the various basis elements that we have for this subspace P2. So what I'd like to do is take this inner product and use it to construct an orthogonal basis for this subspace using the Gram-Schmidt process. So we can apply this same process to any inner product space. It does not need to be Rn. So let's recall how that process goes. So here is our set of 3 vectors that span our subspace. And these vectors are all not orthogonal to each other. In particular, the vector 1 and t squared, they are not orthogonal. So what Gram-Schmidt process says is, okay, pick the first vector. That's going to be my first vector in my orthogonal basis. Then, to find the second vector, we are going to pick the component of P2, in this case t, which is orthogonal to the first vector v1. So the way we do that is we first project v2 onto the subspace spanned by v1. So this is the orthogonal projection of P2 onto V1. And then when I subtract that from P2, what's left over is the component which is going to be orthogonal to V1. So these two vectors will be orthogonal to each other. But we have a really nice situation here. So the way that we calculate the projection of this polynomial P2 onto the subspace spanned by V1, which was the polynomial 1, is going to be some scalar multiple of C1 times that vector, which is 1. And the way that we define this weight, C1, is we take this basis element, P2, inner product with the first basis element, and then divide that by the inner product of the first basis element with itself. So in this case, we get 0 because P2 and 1 were orthogonal to each other. So we actually didn't have to do all of this. I just want to be thorough about it to say that because V2 and V1 are orthogonal to each other, there is no component of P2 which is in the same direction as V1. So this projection is equal to 0, and the second vector is already orthogonal to the first vector, so we are just going to pick the second vector in our for our basis to be t. We probably could have just decided that from the get-go by noting that the second element was already orthogonal to 1, but here's the process that we would go through Gram-Schmidt. And then for the third vector, we do something very similar for V3, and that is we find the component of V3 which is orthogonal to the space spanned by the previous vectors in our basis, in our orthogonal basis. So to first calculate the projection of P3 onto the subspace spanned by the first two vectors, we use this nice formula from the Gram-Schmidt process that says we take linear combinations of the first two basis elements, 1 and t, and the weights that we use are given by these two formulas for C1 and C2. So for C1, the weight for the polynomial 1, we take P3 inner product with the polynomial 1 and divide that by the inner product of polynomial 1 with itself. So in this case, we do not get 0 since t squared was not orthogonal to 1. So we get a 10 on the top, and the inner product of the polynomial 1 with itself is 5. And we do the same to calculate C2. Now we take P3 inner product with t and divide that by the inner product of t with itself. So in this case, we would get 0 divided by 10, which gives us 0. So now we've got the two weights that we need. First weight was 2, the second weight was 0. So this tells me that the projection of P3, which is the polynomial t squared, onto the subspace spanned by these first two vectors is equal to the polynomial 2. So now the third vector and final vector in my orthogonal basis is going to be the portion of P3 which is orthogonal to the subspace spanned by V1 and V2. So I find that vector V3 by taking this projection that we just found as 2 and subtracting it from the initial vector that we had, which was P3. So the third vector in my basis is going to be the vector t squared minus 2. So now we've got a basis that consists of the vector 1 was our first vector. The vector t was the second one, since those two were already orthogonal. But this vector P3 that we had up here was not orthogonal to these first two vectors. So after using the Gram-Schmidt process, we can find that a third vector that we can add is actually t squared minus 2. And so now we have a basis of 3 vectors, 3 polynomials that are going to span this subspace P2, which has dimension 3, where now we're going to choose 1, t, and t squared minus 2. This might seem like a weird choice for a basis element, but this is actually pretty nice because based on the way that we've defined this inner product, these 3 vectors are all orthogonal to each other. And we've already seen in many situations why orthogonal bases are particularly nice to work with. So now we can do this for any general inner product space.